In this example, we're looking at an axial loaded bar with an axial loaded P. We aren't given P. In fact, we're asked to find it. What we know actually is sort of the inverse of what we generally do. We know what the state of stress is in terms of an element which is rotated 45 degrees from the x-axis. We know that if I call those new axes x prime and y prime, I know that sigma x prime is 40 megapascals, sigma y prime is 40 megapascals, and tau x prime y prime is a minus 40 megapascals. So we're going to use that information to work backwards in order to find P. So knowing this state of stress, then we can always go back to our equation that we derived from our stress transformation work and figure out how the two components of stress are related. We know we need this value here, sigma average. So in this case, it's going to be sigma x prime plus sigma y prime divided by 2. That gives you a 40. The r value, that's the sigma x prime minus sigma y prime over 2 squared plus tau x prime y prime squared. So it gives us r. And then from our stress transformation work, and from which we calculated our principal components of stress, we know then that sigma 1, our largest component of principal stress, is sigma average plus r, so that's an 80. Sigma 2, our other principal stress, is sigma average minus r, so that's a 0. And the tau max in plane, which is equal to r, that's a 40. Now what we're going to do is draw a Mohr circle for this. What do we need to draw the Mohr circle? Just two things. We need to know the sigma average, which we've got, because that represents the x component of the center of the circle. And we need to know r, which we have that too, which is the radius. So from that, I draw it, and you can see here from the figure that our radius, again, is r. Our principal stress, sigma 1, that's all the way on the right-hand side. We found that was in 80. Sigma 2 was a 0. And again, tau max there is equal to r, which is a 40. So that just gives us a picture of what we have got. But note that if we look at the way the bar is loaded, there's going to be a sigma x value of normal stress, but no sigma y. So since this is a unit axial load, then x-axis is the principal axis, which means that the sigma x, which is equal to sigma 1, that's equal to P over A. We know the area of the cross section. So from that, we can solve for the value of P by taking that area and multiplying it by sigma x. So again, the problem is given to us in a backwards sense. Typically, you're given P, and you would want to find out what maybe what the state of stress is when you rotate that element through 45-degree angle. In this case, we're given that it's rotated at 45, but we're given the results, and we want to work backwards in order to get P. The equations we use are the same. It's really constructing Mohr's circle by calculating sigma average and r, that's all we need, from which we know the largest principal stress, sigma 1, and that's the same thing in this case as is sigma x.